Hello and welcome to your online lecture for today. So let us get started like we normally do and go over what we talked about on Friday. So we finished up chapter 17 on Friday. So the first section, 17.8, is about how anions are bases and cations are acids. Only certain cations. So if we're looking at metals, group 1 and group 2 metals are not acidic. The other metals are. And so if you add a cation and anion together, you make a salt. And so some salts in water can be acidic, basic, or neutral. Here, sodium fluoride, fluorine minus is a base, sodium group 1 neutral, so that's a base. Iron chloride, iron 3 chloride, iron is transition metal, so acid. Chlorine is not a base, so this is an acid solution. Then we talked about polyprotic acids, many hydrogen acids. These are acids that have multiple Kas, multiple acidic hydrogens, but really we can just ignore the other hydrogens except the first. Ka1 is all that matters. And so when we're doing a problem with a polyprotic acid, we can just lose one hydrogen and we don't have to worry about losing the second or the third. Then the last part of chapter 17 section 10, is how to determine the strengths of acids just by what they look like. So binary acids, as you go to the right of the periodic table, they become stronger. As you go down the periodic table, they also become stronger. To the right is generally more important than down. Oxyacids, as you go to the right, oxyacids also become stronger. But here, as you go up, they become stronger. So the opposite of binary there. And if you have oxyacids that have the same element, so here we have chlorine in the example, the oxyacid with more oxygens is a stronger acid. And with that, let's get into chapter 18. So chapter 18.2. And while watching this video, I hope you are taking notes as I write them down. Treat this just like the classroom. Chapter 18.2 is buffer solutions. So first, we need to define what a buffer is. And a buffer resists pH change. So if I have a solution, and if I say that solution is buffered, then that means that the pH of that buffered solution doesn't change much. And it is made out of weak acid plus its conjugate base. And I can also say weak base plus conjugate acid. All right, same thing really. But basically, to have a buffer, you need a conjugate pair in solution. And so let me give you an actual real life biological example of a buffer. So let's talk about the buffer in your blood. So your cells, while they are making energy, one of the waste products they make is CO2. And CO2 is nonpolar. Remember those definitions back from the beginning of the semester? So CO2 is a nonpolar substance. And to expel CO2 from your body, you needed to get to your lungs. And to travel to your lungs, you have to go through your blood. However, your blood is polar, which is a problem because if we had CO2 in our blood, we'd have little gas bubbles. Those gas bubbles could go to your heart and your brain and cause a big problem. So what your body does to transport that CO2, it changes it into carbonic acid, H2CO3. Now, H2CO3 can break down to HCO3 minus. And this is your blood buffer, right? This is the substance that keeps your blood at a slightly basic pH, like 7.2. And let's see how a buffer would work just using our example. So let's say I had my blood buffer and I added acid to that buffer. Well, an acid that will react with my base in my buffer, the HCO3 minus. Remember, an acid gives a hydrogen to my base. So I would make Cl minus plus H2CO3. I'd remake my conjugate acid. Here, we didn't make any H3O plus, no H3O plus made. So pH barely changes. So pH only changes very slightly. So even though I added this acid, this strong acid to my solution, the pH of my solution really didn't change. And we can look at that same type of behavior when we have a base. So let's say I add a strong base to my solution, NaOH. My base will react with my acid of my buffer. The acid will give the hydrogen to the base. You'll make water, sodium plus carbonic or bicarbonate. And again, here no OH minus or H3O plus was made. So again, pH would only change very slightly. pH would still change, would be very small. So this is showing you how a buffer works. Again, to recap, a buffer is made out of its weak acid plus conjugate base. It's a conjugate pair in solution. And it works by neutralizing any acid or any base that is added. And so let's actually calculate how the pH of a buffer is measured. Let's talk about the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation. And this equation is used to measure the pH of a buffered solution. And it's really quite simple. pH equals pKa plus the log, the concentration of your base. And this is your conjugate base of your buffer. Divided by your acid. This is the conjugate acid of your buffer. All right, so pH equals pKa plus log of concentration of base of your buffer divided by concentration of acid of your buffer. And let's just take a little side journey and talk about pKa. And pKa is something you used in the lab last week. Remember, whenever we see that lowercase p, that is equal to minus log. So pKa is simply the negative log of your Ka value. Remember, Ka is your acid dissociation constant. Right, and so if we just have a generic acid, Ha, so H plus plus A minus, your Ka is simply products over reactants. And so pKa is really a way that we use to compare different acids and see which one is stronger. We don't use Kas, we talk about pKas. Right? And so let's use our Henderson-Hasselbalch equation. And so the slide I am going to do, it's titled section 18.2 together. And it's example 18.1. So this is from your book. And the question is, what is the pH of a buffered solution that is 0.100 molar HC2H3O2 and 0.100 molar NaC2H3O2. The Ka of your acid is 1.8 times 10 to the minus 5. All right. So the first thing we should do whenever we get a buffered solution is figure out what is our acid and what's our base. So we have two molecules. There's a couple ways you can do this. So when I'm comparing my two molecules, my acid will have one more hydrogen than my base. Remember, that's how conjugate pairs work. Another thing you can look for, bases often have a metal. The reason for this is bases are usually negative. And so when you're negative charge, you usually attract something that is positive. So you attract a positive molecule. Metals are positive. So that's why a lot of times you'll see a metal next to your base. So HC2H3O2s are acid, NaC2H3O2 is our base. Right? And I want to know what is the pH of this solution. So we're going to be using the Henderson-Hasselbalch equation. pH equals pKa plus log base divided by acid. All right. So our acid is 0.1. Our base is also 0.1. So this is log of 0.1 divided by 0.100. And I have to find my pKa. Right, so our Ka is 1.8 times 10 to the minus 5. So our pKa is minus log 1.8 times 10 to the minus 5. Our pKa is 4.74. Plus the log of 0.1 divided by 0.1. All right, here's a fast trick for everybody out there. The log of 1 equals 0. So 0.1 divided by 0.1 is 1. So this would be the log of 1. So this is 0. So in this case, our answer is 4.74. Our pH equals pKa. All right, so from this example, we actually learned a couple of things. So let me kind of lay out what we just learned from this example. What we saw is that in a buffer, if your concentration of your acid equals the concentration of your base, then the current pH you are at is equal to your pKa. Right, the Henderson-Hasselbalch equation tells us that. Also, for buffers, some other information. A buffer has a range of plus or minus 1 its pKa. What does that mean? Well, the pKa of my buffer is 4.74 in this example. So that means my buffer, the buffer we have here, will work between the pHs of 3.74 to 5.74. So for this problem setup, if I have this buffer and I'm anywhere between 3.74 and 5.74, my buffer works as a buffer. However, if I go below 3.74 or above 5.74, I will no longer resist pH change. My buffer would be broken. It would no longer be able to do its job, right? So keep that in mind. Keep those two things in mind, actually. If the amount of acid is equal to the amount of base in your buffer, your pH equals pKa. And if you have, and also, sorry, your buffer has an effective range of +1 and -1 is pKa. So as long as you're in that range, you will have a buffer. Right. As always, if you have questions about that, feel free to rewind the video, ask me. Also have Evan, your tutor, can probably help you out with this. BrainFuse can probably also help out with this. But with that, let's go on. And right now I am on Monday's slides. And the first slide for Monday is just simply titled section 18.2. And these are Henderson, Hasselbalch example problems. So I'm not gonna spend time in this video going over them because we just did that. But if you would like more practice, go see this slide, try out these problems. If you try them out, feel free to ask me. I can take a look at them, tell you yay or nay. Ask BrainFuse again. That's a totally free tutor for you. Your AI on your textbook might be able to help. I haven't actually checked that, but you can see, I can definitely verify for you. But what I want to go on to is the next slide. This is still 18.2, and this is how to calculate pH changes in buffers. Right. And those slides walk you through how to do it. And I'm gonna kind of walk you through those slides by doing a problem. So I can show you the steps in motion for a real example. So let's do example 18.3. This is a problem for your book. And this says you have a 1 liter sample or 1 liter solution has 0.100 moles HC2H3O2 and 0.100 mole NaC2H3O2. So it's the same buffer we just saw in our previous problem. The Ka for HC2H3O2 is 1.8 times 10 to the minus 5 And it's actually giving us our pK already is 4.74. So right now, let's just take a look. So this is our acid. This is our base. We have 0.100 moles of acid, 0.100 moles of base. So right now, our pH equals our pKa. And the question is, what is the pH if I add 0.010 moles of NaOH? All right, so we have to figure out the pH. So first step one, when we are doing a problem, when we are adding something to our buffer, write the reaction of how the added, in this case, base will react with your buffer. So NaOH is a base. And so a base will interact with our acid, right? So that's how it's always going to go. If you add a base, it interacts with your acid. If you add an acid, it interacts with your base. So let's see this. So our acid gives a hydrogen to our base. And we make Na plus H2O liquid plus C2H3O2 minus. All right, so that was step one. Write the reaction. Step two. I'm gonna do a different color pen here. Step two. Write an ice table. Remember, ice tables initial change equilibrium. All right, water is liquid. I don't care about you. All right, let's do initials. So I added 0.010 moles of NaOH. Initially, I have 0.100 moles of HC2H3O2. How about my initial sodium? Now, if you're following along, I'm going to guess you would think to put a 0 there. But let's take a look. In my buffer, I have 0.100 moles of NaC2H3O2. All right. So remember, metal is a cation. Non-metal, carbon, hydrogen, oxygen, these are non-metals. These are anions. So when a cation plus an anion or a metal plus a non-metal are interacting, that is an ionic bond. This is something we learned back in General Chemistry 1. If I put an ionic bond in water, that ionic bond breaks apart. And so you get sodium plus C2H3O2 minus. So if I have 0.1 moles of this compound, that means when it breaks apart, I get 0.100 moles of sodium and 0.100 moles of acetate. So my initial concentration of sodium is 0.100 moles plus 0.100 moles of acetate. All right, so that's our initial. Now we have to do the change. All right, so here we have a base interacting with an acid. Remember when a base plus an acid interact, they will neutralize each other. That means they will completely react. They will always react. So I'm going to lose my base. I'm going to lose my acid. So my reactants are going to react. So I'll gain product. Oops, that's supposed to be an X. Gain product, and I'll gain product. Okay. So for our ice table, usually we do I plus C equals Z, and we are going to do that. But before we do that, for a buffer, we need to figure out at X. So I have to know what the numerical value of X is. And this is a limiting reagent problem. This is another topic back from Gen Chem 1. Yes, in Gen Chem 2, we have to remember what we did in Gen Chem 1. All right, so let's just kind of make a silly example. Since last week was National Burrito Day, it actually was. Let's do our example with a burrito. So let's say, and I'm sorry, I'm going to make this smaller because I don't know how to move around so well. So let's say I do an example with, I guess I can do it down below. So let's say I'm going to do a burrito equation. I'm going to make it very simple. A burrito is made out of one tortilla plus 2 pieces of chicken plus, I don't know, 3 pieces of lettuce. It's a very sad burrito. Makes one burrito. No beans, no cheese. And we can do an ice table for this. I know you never thought you'd be seeing an ice table for a burrito, but here we are. Okay, let's say I had, I don't know, 15 tortillas on me. I had 8 pieces of chicken. I have, I don't know, 20 pieces of lettuce, and I have not made any burritos yet. And so the question is, how many burritos can I make? So I'm going to lose some tortillas. I'm going to lose 2 pieces of chicken every time I make one burrito. I'm going to lose 3 pieces of lettuce every time I make a burrito. And I'm going to gain 1 burrito. So the question is, at equilibrium, how many burritos do I make? Again, this is a limiting reactant problem. All right, so which one runs out first? The tortilla, the chicken, or the lettuce? And the answer is the chicken. That's my limiting reactant. I can use all 8 of my chickens. So if I use all 8 of my chickens, I would have 0 left over. 8 minus 2 times 4 is 0. So X is 4, because that's the thing that runs out first. So that means that at equilibrium, I still have 11 tortillas left over. I'm out of chicken now. 3 times 4 is 12. 20 minus 12 is 8. I still have 8 pieces of lettuce, and I was able to make 4 burritos, right? So that's a limiting reactant problem. That's the same way an acid and base reacts. So I have 0.010 moles of base, and I have 0.1 moles of my acid. Well, my base runs out first. Right, so X is 0.01, so minus 0.010 minus 0.010 plus 0.010 plus 0.010. So this is at equilibrium, you have no base left. You have 0.110 moles of acid. You have 0.110 moles of sodium. And you have 0.11. Whoops, I did my math wrong. You're all probably screaming. All 5 of you who made it this far in the video are screaming at me. 0.090 moles of acid and 0.110 moles of base. Right, so we found out what our limiting reactant was. Then we subtracted that from our equation, or from our ice table, sorry. Now we are ready for step 3. Step 3, this blue looks nice. We can use the Henderson-Hasselbalch equation. pH equals pKa plus log of base divided by acid. Remember, brackets equals molarity, which is moles divided by liters. Right now, our acid and our base, remember, always keep straight what's your acid and base. But right now, our acid and base are in moles, so I need to divide by the volume. And I'm saying the volume is 1 liter. So I'm going to take my acid divided by 1 liter. Take my base divided by 1 liter. And so pH equals pKa, and we were given the pKa already. pKa is 4.74. pH equals 4.74 plus the log. Our base is 0.110 divided by 1, which is 0.110 divided by our acid, 0.090. The reason why this works out, again, 1 liter, anything divided by 1 is itself. So let's do this. So the log of 0.110 divided by 0.090. And I'm going to add that to my pKa. So my pH is 4.83. So my pH went up a little bit. That's totally fine. It didn't go up that much because my buffer neutralized the buffer neutralized my solution. All right, so let's do one more problem. We are gonna do, and it's called on the slides, section 18.2, more practice. And this says a 250 milliliter buffer is 0.250 molar acetic acid and 0.250 molar sodium acetate. pKa is 4.74. So it's the same system we're using. So let me actually give you the formulas. Acetic acid is C2H3O2. sodium acetate, Na, C2H3O2. All right, and the question is, we're gonna do part B of that problem. I'm just gonna skip right to it. B, what is the pH after the addition of 0.0050 moles of HCl? All right. So if you want to do well on the next test, follow this advice. Pause the video, try it, see how far you can get. Right? Look back at your notes, look what we just did on the last problem. This is now your time to struggle. By struggling, you will increase your knowledge. I guarantee it. You will remember this when it comes to test time. But pause and try it. I'm actually going to go through it right now. So I hope you have the solution in front of you, or at least as best as you could. So let's follow our flow chart from the last problem. Step 1, I'm going to write down my equation. So I have HCl. So that's going to react with my base. HCl gives a hydrogen to my base. So I make Cl minus. That sodium pops off as well. And I'm going to remake my conjugate acid. Right, so this was my base. This is my conjugate acid. Now let's make our ice table. All right, so let's start with initial concentrations. Now, this one might have tricked you up if you weren't paying attention. 2 of your units are in molarity, but the HCl was in moles. So when you're doing an ice table, you want everything to be in the same unit. So what I'm going to do first is I'm going to convert HCl's to molarity. So that's kind of a hidden step there. It's tricky, but just remember, keep everything in the same units. So HCl, we have 0.0050 moles of HCl. And the problem says our solution is 0.250 liters or 250 milliliters. So 0.0050 divided by 0.250. Our molarity of HCl is 0.020 molar. So that's our initial concentration. Our base is 0.250. We don't have any chlorine. We can say we don't have any sodium, but we can also write it down like this and say we have 0.250 of sodium. It really doesn't matter. The sodium's not doing anything in this reaction. And then our acid, we have 0.250 molar as well. Right now we're in molarity. So again, we have a limiting reaction problem. We have an acid interacting with our base. So we pick the smaller number and we subtract minus 0.020 minus 0.020. Here on the products, we're going to add 0.20. And we're going to get 0 here, 0.230 base, 0.020 chlorine, 0.020 sodium, 0.270 acid. Right, then we do Henderson-Hasselbalch, step 3. pH equals pKa plus log base divided by acid. pKa was 4.74. That was from our problem. Plus the log of base. Our conjugate base is 0.230 divided by our acid, 0.270. All right. So there we go. Thank you for moving. Oh, Zoom. Why are you doing this to me at the very end of the lecture? Well, there we go. So equals log of 0.230 divided by 0.270. I'm going to add that to my pKa of 4.74. And so 4.74. And so your pH is 4.67. So we added a strong acid, our pH went down, but it didn't go down that much, right? That's the power of a buffer again. So I hope you did try that to figure out this problem, how to deal with buffers and adding acids or bases. This is going to be big for our next section. So our next section is titrations. So if you have any questions about this, please let me know. Otherwise, I hope you're going to be able to see the eclipse. It is pretty cloudy. If you're watching this after the eclipse, I hope you didn't burn your eyes out. And I will see people on Wednesday. Take care, everybody.